Okay, just to make things easier on me in terms of editing, we're going to try and do this all in one take. So, progress update on Deep Thought. Initially I was working with this model, and I did in fact get the ALU and registers installed. There is a problem that I encountered though, and that is because we're actually designing it from the top down, we've got the program memory in the top, processing circuits in the middle here, and I've just frozen here. There we go. Finite state at the bottom, and then I/O and memory at the very bottom. All of our wiring is vertical, and what's worse is all of our wiring is flowing down. So that is not at all the most compact method of doing it. Anybody who's worked with downward, direction vertical wiring will know that it's not at all compressible. So what I've done is I've redesigned the ROM, or the program memory, depending on how you want to do this, and it's basically vertical now. And so what this does now is the buses that come out from the bottom can now be placed out vertically, which is much more efficient and a lot easier to work with in terms of compression and such. Now, as far as the ROM changes are concerned, there are pros and cons. The pros are it's a very nice user interface. You can see everything right there. And it is stackable. This particular slice can be stacked out 8 times. Con is it also has vertical wiring, and of course, its vertical wiring is torch-based. Yeah, I tried going with a spiral. I just couldn't get it to fit and go to every other block, because most spirals will usually go to every third or every fourth block. Getting it to go to every other block is just a real challenge. And I've gone and frozen again. Seriously, Mojang, please fix the frames. Freaking hell, dude. Okay. Sorry, just small rant. So anyway, this thing is torch-based, so it does take a little bit of time between each instruction to actually get the instruction to the finite state machine, but because it's stackable, you can stack out this way, and that of course will be connected through a proper bus. You can decrease the time a little bit, I guess, between instructions like 16 and instructions 127, if that makes sense. So I basically tried to overcome this as much as possible by making this stackable. And that said, like I said, it is stackable, so there's 16 instructions. I think I said this already, maybe not, but there's 16 instructions in this bank, and this can be stacked 8 times, making for a grand total of 128 instructions. Now you might be thinking, how can there be 128 instructions? I thought this was a 6-bit bus. That was another change. This is now a 7-bit bus, and in the original design here, you'll see more frame spikes. Christ. Okay. You'll see that the data bus is separate from the address bus, and the address bus is 6 bits. In order to actually squeeze the addressing bus over here next to everything, I actually had to combine the data and address together. So what we've got is, instead of data 0, 1, 2, and 3, and then address 0, 1, so on and so forth, what we've got is address data 0, address data 1, address data 2, address data 3, and then address 4 and 5. What ended up happening was, because I had that set up, I had space for 8 bits over here and 6 bits being used over here. So what I did was I just split the difference. I've got now a 7-bit input here and a 7-bit address bus over here. So this makes for double the program memory, but it also means I can double the RAM and the ROM as well, considering that now all that is 7 bits as well. Or sorry, RAM and I/O. So I can now address up to 128 instructions, 128 memory locations, and 128 I/O devices. So not too shabby, if I do say so myself. Anyway, as for the wiring itself, this is a little bit sporadic right now, but that's just because I'm still designing everything. But what we've got is, we've got over here in this corner, we've got the address processing circuits here, the data processing circuits here, which is the ALU, the accumulator, and the flag register, as well as the flag decoder. And these, combined with the program memory, take up only 25 blocks out of my 40 blocks, basically, which leaves 15 blocks for space, really. So what I'm intending on doing is I'm taking all this control circuit, circuits right here, squeezing it into this area right here, with the idea that the whole thing is cut short at 25 blocks. Now, that does not mean that the final dimensions of this computer will be 40 by 40 by 25, and there's a plane going overhead. That is loud. This does not mean that the final dimensions of this computer will be 40 by 40 by 25. What this means is that the actual processing side of the computer will be 40 by 40 by 25, with a 40 by 40 by 15 area reserved for memory and I/O. The idea of this computer is to be self-contained, so it will have a fairly substantial but still small amount of memory on hand, as well as a few I/O devices, with a bus port extension right at the 40 block mark, sticking out with the intention of the user, if needing be, the ability to attach more RAM and more I/O. And like I said, of course, because the program memory is expandable, you can also expand the I/O, or the program memory slots. So even though this thing is really small and really simple, it's expandable, and it gives it a little bit of flexibility with that. Anyway, next thing that's changed, I guess, is the frames. Apparently, I'm down to 30, which means we're probably going to get a lag spike here. Yep, there it is. Back up to 60. Wow, this is nuts. So, back down to 30. I'm sorry, I'm trying to get my thought out here. So what we've, I guess, I don't know. I finally finished the finite state machine for all this, as well as the majority of the control circuitry for the whole system, which means, technically speaking, this computer is functional. I just don't have any memory or I/O to work with, but I do have program memory, and it does have all 4 or 8 of its instructions working, depending on how you look at it. And the finite state machine, I never really went into details of it in the last video. That's because the concept is fairly simple. I just didn't quite have a map as to how this thing will flow. So I do actually have a map for this, and it is programmed, and I'll have that up on the screen, hopefully. Maybe not, I don't know. But I can explain how it works properly, I guess, right now. I just want to warn you, conceptually it's simple. Applicantly, I guess it's a little complex, and there's more lag spikes and such. So let's do our best to explain how this works, shall we? So, as I said, there are 4 instructions. In the previous video, there are 4 instructions. There's the move, load immediate, control, and jump. What move does is there's basically 4 instructions there. Move basically works with just the accumulator and memory, or I/O, depending on how you look at it. So you can, of course, either move in to the accumulator, or you can move out from the accumulator. So those are 2 instructions. And then you can move from or to memory, or from or to I/O. So that's another 2 instructions. So you basically have 4 combinations. You can move memory to accumulator, accumulator to memory, I/O to accumulator, or accumulator to I/O. And of course, that's all controlled by the address bus down here. So you can use the address bus to address memory locations or I/O devices, and then of course the last bit that the last bit controls whether it's I/O or memory. And so basically the way this instruction is set up is the first bit, if it's a 0, it's a move, and then the next bit will control whether it's in or out, and the last bit will control if it's I/O or memory. So that gives you a total of 4 instructions right there, if that makes sense. Like I said, there's conceptually it's simple, I guess. I'm just doing a little bit of a terrible job explaining this. But another feature of this is the in instruction, whether it's from memory or from I/O, actually takes into consideration a function as well as the accumulator. So when you bring data in, it actually doesn't go directly to the accumulator, it goes through the ALU, so you do have to assign a function. Reading the accumulator will clear it, so if you read it, it'll clear, and then if you OR, you'll basically be ORing whatever's data's on the input with nothing. So you basically get the data itself, and you can put that back into the accumulator. This means that you can do arithmetic as well as loads at the same time. So say I have a number in the accumulator, and I wanted to add a number, I could bring data from memory into the accumulator, or into the ALU with the function set to sum. Then I can take the result and put it back into the accumulator. So that just saves instructions. I don't have a need for arithmetic or logic instructions as a result. And then the next instruction, I guess, is the load immediate instruction, and that instruction is 110, and that is fixed. You can't. There's no options there. That's one instruction. So load immediate basically takes the data from the 4-bit data segment of the program memory and moves it directly into the accumulator. And of course that takes an operation as well. So this is basically just a load immediate or operate immediate, depending on how you look at it. Control is working, but there's nothing connected to it. Control basically just clocks, where is it? This line right here. And so the idea is that you would have 2 bits that dictate that. So you, come on, stop it, lag. Stop it, lag. Okay, you basically have 2 bits. You have a 1, 0, and that tells the computer that it's a control. And then if this is 0, it's a reset. If it's a 1, it's a set. But of course the finite state machine doesn't take that into consideration. It basically ignores that bit. All it does is it latches this, and with that latched and that in whatever state it's in, you can basically use that to set or reset a control flip-flop. And then you can use, I haven't decided whether I would use the data bits or the address bits, but you can use those to select what flip-flop you're setting or resetting. So for example, I could use that bit to set a halt flag, and that would then send a wait signal into the finite state machine and effectively stop the computer. So that's one application to that. You could also use it for SID or SOD purposes, serial input or output data, setting carry flags, but I don't have that implemented because my flag register is primitive. And then the last instruction is a jump, and that's just ones across the board. That's a jump, so that takes into consideration the data on the 7 bits for the address. And jump is actually conditional, so I should probably mention that here. So these 3 bits here, they dictate the function. Remember when I said load immediate and move take a function? These also control condition. So there are 4 conditions. There's carry 0, sign, and then always on. And then the 3rd bit can negate it. So we can either choose carry or not carry. We can choose sign or not sign, 0 or not 0, and then always or never. And so those 3 bits are taken into consideration as well as the flags, which produce a signal, and if the condition is true, the signal will be on. So that then goes into the finite state machine. So if all 3 bits are a 1, it's a jump, and if that's on, it will successfully perform the jump, and what that will do is load the data from the address bus into the, come on, program counter over here. And so that's how you would branch through your program. So that was one thing that I wanted to include. Most simple programs are very linear, or most simple computers in Minecraft are very linear in that you can only perform instructions one at a time. This was something that I was adamant about including, was conditional jumping. I wanted to have branching like calls and returns, or even stack frames and stuff like that, but of course, like I said, I just didn't have the room. So conditional jumps work, but that's, you know, that's fine. That's pretty much all you need to make a Turing-complete computer, more or less, I guess. Sort of. I don't know, because you still need to be able to call subroutines, which I guess is not something that my computer can do. So maybe my computer's Turing-complete, maybe it's not. I'm not sure. But yeah, all that said, I should mention that, you know, at this point my finite state machine controls signals directly from program memory, so it actually has a library setup of instructions installed. If you're doing a larger computer, this would not be the case. What you would have is you'd have the finite state machine perform a set loop, which would include update address, read, write, and some 4th thing, and then you'd have a lookup table feed it parameters. So you wouldn't actually have the finite state machine hold the parameters for instructions, but in this case, because my instruction set is small, I can do this and get away with it. So basically, I'm going to do my best to explain this with the image on the side here so you can follow along. But what we've got is we've got a finite state machine with 7 states. And so the 7 states are the reset state, the address update state, the wait state, and then the 4 instruction states, which are labeled T0, T1, T2, and T3. By default, if the reset line is on, it will go to the reset state, which I believe is state 0. So you can see now these latches, I guess, are all in 0, so that shows that it's in the reset state. Coming out of the reset, or going into the reset state, basically what it looks for is if it's in the reset state and the reset is on, it's going to go to itself. If the reset is off, if I can get to it, if the reset is off and it's in the reset state, it will go to the wait state, which is TW, or TWait, which is 1, as you can see. And of course, the transitions occur on the rising edge of the clock, so that's why the clock is there, and that's why it's running. Yeah, so from there, the wait is actually what takes the information from the program memory and decodes it. So in the wait state, it can basically look at these operation inputs and go, okay, is it a move instruction, a load instruction, control instruction, or jump instruction? And based on those that information, and of course whether or not it's not reset, it will go from wait to either T0, T1, T2, or T3. And if it's a T0, T1, or T2, which is move, load, immediate, and control, it will perform its function, which basically what that does is it takes the information from the register that's controlling the current state, goes into a decoder, and then latches certain lines. So it will latch the lines, and then it will go from that state to T address, or TA, and what that will do is it'll increment the program counter over there. And then of course from TA it'll go back to TW and start the cycle all over again. T3, however, is the jump instruction, and because we've already updated the program counter with our current address, we don't want to increment the program counter because that will go to the next program prematurely, or the next instruction prematurely. So what we do is we actually go from T3 right back to TW, and I can actually demonstrate this. I believe it's on address 3, so 0, 1, 2, 3, if I were to do that. Now it's in it's currently in TW, or sorry, yeah, it's in TW, and it's waiting at this point with the address, or sorry, with the function being a jump, and the condition is true. So if I were to go ahead and step this, you'll see what will happen is it will jump to an address, and then it'll go back to the wait state. So it'll go to, if we can catch it, it'll go to the PC latch, and then it went back to wait. So if I were to perform some other instruction, like here we've got another instruction, it will actually go to the PC increment state and then back to wait. So it'll latch, accumulator read, PC increment, memory write, and then wait. So that accumulator read and memory write are actually part of the same cycle, or the same state. It's just one happened on the rising edge, the other happened on the falling edge. That's why PC increment happened before. But that was basically 3 states. So the nice thing about this is pretty much every instruction, depending on how you look at it, takes 2 to 3 clock cycles. So it's pretty fast, I'm not going to lie. And of course, I did my experimenting. I can basically have a clock speed of about, let's see, 3, so that's 6, 7 ticks before it becomes unstable. So any faster than that, and it starts to lose data. So this is basically the fastest, or slowest, I guess, fastest I can get it before it starts getting into trouble, which is still pretty fast, I won't lie. And then lastly, I guess the last thing I want to show you is the stepping function, which you just saw. So this finite state machine has a wait line, and basically what this is at TW, or TWait, it will take into consideration the wait line, and if it's on, it will stay in place. If it's off, it will continue on to its next T state. And this wait line basically counts for everything. So it can be the wait from memory, which is where the memory doesn't quite have its data ready yet, so it'll enable the wait and tell it to stop. It can also be used for stepping, and a third line will of course be introduced for halting. which is what I mentioned earlier. There will be a halt flip-flop, which can be controlled by the control instruction. But in this case, I basically just got the circuit for stepping, which is fairly simple. So the way this works is at TW, it actually sends out a signal on the wait line, and so the wait line goes into a inverted monostable circuit, so it's basically looking for a falling edge. So only when it goes out of the wait state will it actually trigger this. And what this is a RS NOR latch. And so what we've got is we've got the wait line which comes in, and when you turn this on, it will go to an AND gate, which of course is the other side of the AND gate is the RS NOR latch, which, if that's off, will of course not send a signal, but because it's also checking for a rising edge and latching the RS NOR latch, it will turn on, automatically latch that, and that will be enabled. Because this is a rising edge, of course I can leave that on, it won't affect it, which means when I press the button, it will set it, or reset it I should say, which will disable wait, and because wait is now disabled, it will go to the next T state. But of course, as soon as it goes out to the next T state, this line turns off, and this line is designed to check for a falling edge. So as soon as it falls, it activates this monostable and sets the latch again. So I know that was a bit confusing. I'm really not that good at explaining this stuff, but that was basically just a very, very, very simple step system, I guess. So basically, instead of stepping through each clock cycle, we're stepping through chunks of clock cycles per instruction. So this just makes it easier to single step and debug the computer, which I've been using a lot to try and debug the instructions. But yeah, I'm really not sure what else to say. I basically went through everything, as well as some basic theory of the finite state machine. So I guess that's it. Yeah. I know this was a little bit confusing. I'm really not sure what it was I was trying to say the whole time. I was just kind of making it up as I went, but hopefully you got something out of this video. I know a lot of people watch my videos to learn something, and that's great. I'm glad I could contribute to people's knowledge bank. That's always great to hear. So hopefully you guys learned something, and I'll be sure to catch you guys in the next video, when hopefully I will have all this stuff compressed and squeezed into one side of the computer, as well as given some RAM. So yeah, thanks for watching, hope you enjoyed, and I'll see you in the next video. Bye!